lecture 17. So today we will discuss blocks, but before that we will briefly recapitulate whatever we did in the last lecture. So here is the grammar of the language, and the most important new construct is mixing declarations within commands, and that creates a block with a local declaration. Blocks are like unnamed procedures as far as this language is concerned. They are purely local, they cannot be called from elsewhere. However, you can nest blocks. So we define locations as an infinite collection. We define lock as an infinite collection of locations, and stores is a function from some finite subset of locations to values. Stores over L is such a thing, and the set of all stores is over all finite subsets of locations. Environments are now locations become values that can be stored, and so an environment is a mapping from identifiers to either values or locations, where the identity as to whether it is a value or location is preserved in the mapping. Yeah. Okay. So I spoke briefly about uninitialized variables and the need to introduce a new undefined value, and which means that we also have to impose strictness conditions. So expressions evaluated with some sub expression which leads to an undefined value would all be undefined, and would that, pragmatically speaking, would just lead to a runtime error. And we said that we required a new function which, given a finite collection of locations, produces a new location from this infinite collection block, and there are very simple ways of implementing the availability of a new location. Okay. So basic semantics in transition systems is that any expression, declaration or command is evaluated in a given environment with a given store. So the state of a computation in such a language consists of both an environment and a store, right. So the concept of state, which has so far been sort of abstract, is more concrete now. It consists of both an environment and a store. So it's still, we are still talking about languages which are state based, right. Only the notion of state has to be more refined. Here the expression semantics, as I said, the only difference is between in this language, of course, all expressions, we look upon all expressions as basically those occurring on the right hand side of assignment statements. So here are all the there are R value evaluations of expressions. So given any identifier, if the environment points it out to be a constant value, then that is what this evaluation gives us, and if it is a variable, then the environment should give you the location, and the store for that location should give you the value, right. So this is, so there is a level of indirection here for variables. Okay. So let us quickly look at constant declarations. So if you assume that there are no side effects in expression evaluation in our language, then you evaluate the expression through the expression language several times till it reaches a value, and the effect of this constant declaration in a given store is to merely create this new environment, new little environment with the same store. If expressions could have side effects, then what we would, then there is a very simple change that you have to make, it only means that you cannot assume that in the process of evaluation the store remains the same as when you started the evaluation. So what it means is that with each application of a single step of the expression evaluation mechanism, your initial store sigma L goes to some sigma L prime, and it could keep on changing till some final, and so correspondingly what it means is that this declaration also moves to sigma L prime, and eventually when E sigma L moves to M sigma L prime, then this declaration moves to the creation of this new little environment and a modified store sigma L prime. So under the assumption that there are no side effects in expression evaluation, the stores are maintained, otherwise in general they do not have to be. Right. A variable declaration on the other hand is anyway guaranteed to change the store, because it really changes the very function. By adding an extra location, it really changes the very function, that from sigma L to a sigma L union the new location, and the effect of a variable declaration is to obtain a new location which hitherto is not present in L, and bind the identifier to that location with a new initial value for this location, which in the case of this particular language it is the undefined value. Yeah. So the other declaration rules are similar. The effect of this expression language is most importantly felt in the assignment, and the effect of this, so given an environment rho and an assignment statement of the form I is assigned E, again we are assuming that there are no side effects, so which means the evaluation of this expression in 0 or more steps. 0 is important because this expression E could just be a constant value, right. In 0 or more steps could lead to some value M in the store sigma L, and the effect of this assignment is to just change the store to accommodate this new value M in L. So whatever may have been the previous value contained in L is erased and a new value is stored, right. So where of course the environment gives you the location which has to be updated, right. And if there are side effects in the expression evaluation, in general all that it means is that the store could also change in the process of expression evaluation. So if you have a changed store from sigma L to sigma L prime in the process of expression evaluation, then the new store is whatever is there in sigma L prime updated with this new value, right. So the other expression rules and declaration rules and command rules are simple modifications to take care of environment and store from whatever we have previously done. So now let us look at blocks, right. So a block, so we could look upon this block semantics in this fashion. A block is a command in our language, and the first step is to elaborate the declaration in the block. So if this declaration D, and for the moment I am assuming that this declaration D is non-empty, okay. So if this declaration D goes to some D prime, and I am considering a more general setting, your initial state, your initial store sigma L could be changed in several ways. In the process of elaborating a declaration, the store anyway gets changed because new locations might be added. Further, if that declaration contains some expressions which could create side effects, you could have changes in store because of that too, okay. So both, so the store changes for the store could change for two reasons. One is that new locations are added, so the L changes to L prime and therefore the store changes, but in addition if there are side effects in expressions in the expression evaluation mechanism, then those changes could also be incorporated in the store, right. And the result of this block declaration is to just move from here to here, and this rule might be applied several times, and the effect of this entire block is again as usual we will in our language for specifying the semantics we will introduce pseudo commands of this form which are not there in the original language. Just like we did in the case of declarations, we introduced environments also as part of the declaration syntax in order to facilitate an easy expression an easy rule for evaluating declarations. Similarly, for commands which have local declarations, we assume that an environment has been created and a new meta syntactic category of this kind also exists in the command in the command language for the purposes only of specification. So, by the command rules, the effect of this is that this command C is executed in this updated environment, in this temporarily updated environment. So, if the effect of a declaration after several moves in the declaration semantics finally gives you an environment, a little environment rho prime, then C is executed in this modified environment to reach some C prime with some changes possibly in the store, except that your original in C itself, unless C so in C itself the locations that are preserved, it is the same location set, but the store might be changed because of updations of values. So the effect of this the effect of this is to look at this execution in this updated environment and model it as the eventual effect of the block, right. Now this C could be, this rule could be applied several times. So and eventually eventually you will find that what must happen is that when applying this rule, the important question is that you are starting off execution in a store sigma L, but when you are executing this C in this updated environment, your location set could be modified and therefore your store could be different. So sigma L prime is not the same as sigma L, except that for all locations that are common to both L and L prime, they yield the same values, right. So since we are interested only in the execution of this block with the starting store of this form, and we are temporarily updating the environment, and the updation of the temporary updation of the environment also means a temporary change in store, a temporary or a permanent change in store, but this change in store is just that whatever locations are not present in the original store might have some values, but all the locations that are common to L and L prime should have the same values, okay. And so the effect of, and similarly in the final store, since the creation of the locations L prime minus L is temporary because of this, the creation of this little environment which anyway is reversible, therefore this store also reverts to this where the original set of locations are preserved. So the irreversible changes in store are anyway subject to a certain scope rule, so they have a lifetime. So all the locations in L prime minus L prime is a larger set than L, are really temporary because this environment rho prime is temporary, right. So the main constraint in all these 4 stores are these two. For all locations that are common to L and L prime, sigma L and sigma prime L should have the same value, sigma L and sigma L prime should have the same value, and similarly sigma prime L and sigma prime L prime should have the same value, right. Okay. And lastly, once your again with the same constraints on sigma L, once your command in this updated environment finally produces a store of the form sigma prime L prime, then the effect of this entire command on starting from a given store sigma L is to produce a new prime sigma L, is to produce a new store sigma prime L with the same set of locations as it started out with, and sigma prime L is really the same as sigma prime L prime, except that all the locations in L prime minus L have been removed, have been deleted, right. The fact that it's I mean, so it's fairly precise and it's very concise, so it's also dense with information. So there is a lot of information in this rule, right, in the block rules. Okay, so what these rules have shown is that there is some relationship, for example, between environments and stores, which has to be maintained at runtime. The stores, updations of stores can occur because of two reasons: the creation of new environments or just updation of the current store, right. So it's good to specify various kinds of constraints on what happens if some of these constraints are not met, right. So a standard problem, so one thing is that if I were to just take an arbitrary environment rho on a set of identifiers ID and an arbitrary store sigma on a set of locations L, then the question is what kinds of relations do they satisfy, right. So one thing is that every variable that is in ID should have a location corresponding to it, and so only if every variable has a location corresponding to it, so that is one thing that you should have. And secondly, every location in sigma L, every location in L is meaningful only provided there is some variable associated with it, there is some variable bound to it. If there is no variable bound to it, then there is absolutely no way of the program can access that location, right. So the main questions are, does every variable have a location bound to it, and secondly, is every location bound to a variable. And what happens with a lot of normal programming, especially where storage is dynamically allocated, that means at runtime by a user, is that one frequent problem is that you get dangling references, right. So this typically, so what is a dangling reference? So given a state which consists of an environment rho ID and a store sigma L, if there is some location L which is bound to an identifier in the environment, but that location is not present in the store, then what it means is that there is an identifier which really is not part of the program state, okay. So this is known as such a location L is called a dangling reference, okay. This, as far as I can see, is the most precise and concise way of explaining a dangling reference, and this usually happens when you allocate storage to some variable and then you dispose it off while it is still in use, and it can be complicated these matters can be significantly complicated when you have aliases for the same location. That means, when you an alias is when a single location is bound to two different identifiers, then you would say that that location is aliased. So, it is quite possible. So, the effect of aliasing is that you might if there are two identifiers P and Q which refer to the same location, then you might dispose of P even though Q is still in use in the program, and this is something that frequently happens with pointer references in most languages. Yeah. So, this is a storage insecurity. So, a simple example is of this form. You actually there are two pointer variables, let us say P and Q. You have allocated a new location to P, you have assigned that P to Q, and then you have disposed of P. Okay. This kind of elementary programming is often caught by the runtime system, but there is no reason to suppose that this is the only possibility. You could have very complicated possibilities, very complicated assignments, and you might be doing disposals and creating dangling references thereby, right. So, the second thing is, when you have, supposing you have a state, a location which carries a value, but that value is inaccessible, right. So, typically what you are saying is that this location L, this set of locations L has some location which is not bound to a name, right. So, if it is not bound to a name, then that location is inaccessible. This again happens with dynamic allocation of storage, right. So, you have an identifier, you do not have any identifier by which you can access that location, then you would say that it is an inaccessible reference, right. The notion of dangling references and inaccessible references in such storage insecurities actually also translates to when you have a more complicated language and your L values are themselves expressions, could be compound expressions. That is when it really makes sense. With our programming language, with the way we have defined it, one important property you should be able to prove is that there are no dangling references and there are no inaccessible locations, right. Okay. So, one typical instance again with dynamic allocation is that you might actually be using the same name to create new locations, and this creates a new location which is not assigned to anything, and this new allocation overrides this previous allocation, and therefore the previous allocation becomes inaccessible, right. And it's often quite difficult to debug a program with pointers, mainly because the allocation is being done by user, and the user has to be very careful about making sure that there are no inaccessible references or no dangling references. I mean, the onus is on the user to ensure that he does not create them, right. Okay. So, we have actually seen two kinds of blocks in a command language, and the PL0 compiler calls such things blocks, except that in the PL0 compiler every block also has a name. The way we have treated blocks here as unnamed procedures which cannot be called from elsewhere is a simplifying assumption, but is very similar to the let construct in ML, right. You have a let some x equals something, you have some let, some declaration in some expression, right. So, it is very similar to this let construct. So, we can think of this let construct also as a block, right. So, it is a functional language. So, there are no commands, there are only expressions, but these expressions are qualified by declarations or by definitions. In a functional language you call them definitions rather than declarations, but we will use the two terms interchangeably, right. So, our notion has an analog in a language like ML. So, what it means is that you can qualify expressions with declarations, you can qualify commands also with declarations. Okay. And the next question is, can you qualify declarations with declarations, right. So, the only operator on declarations that we have used, if you look at declarations in their pure form, the only operator we have used is what might be called the sequential composition of declarations, right. But there is absolutely no reason why what can be done for expressions and for commands cannot also be done for declarations. And in fact ML actually has these facilities. So let us look at some more aspects of declarations and the creation of blocks, right. So, I am using a loose syntax for brevity, I do not want it to be as complicated as an ML declaration. So, we might consider the following kinds of declarations. So, most of these imperative languages actually allow only one kind of operator on declarations, and that is a sequential composition of declarations, right. But ML has also this, what is known as simultaneous declarations, and it has a construct which I mean, in order to be consistent with this syntax I use the word within, but a typical ML syntax would be of this form. So, what I write as D1 within D2 would actually be written in ML as local D1 in D2 end. It is different from the let construct. Remember that the let construct has an expression here. So, it's a grammatically different category, it is also semantically a different category, right, because a let construct like this actually denotes a value, right, whereas a local construct like this in ML actually denotes an environment. So, the two things are different, and so you reflect their difference by having different syntax too, right. So, the reserved word local in ML is used to distinguish what constitutes an expression block, to distinguish an expression block from what might be called a definition block, right. So, this within construct that we will just call it within. So, it carries this analog of blocks from declarations so you can qualify commands with declarations, you can qualify expressions with declarations and create expression blocks or command blocks, and you can qualify declarations with declarations and create a declaration block. And there is absolutely no reason why this is not, for example, used in for example, why we cannot introduce these new declarations into our original language and give us semantics, because these things these constructs are completely orthogonal to whatever is there in the command language. So, you could take that command language and add these declarations also, these kinds of declarations. Yeah. So, a typical ML program would consist of such all possible such declarations. Yeah. So, we will just call them this is of course sequential, this is simultaneous, and this is nesting of declarations. So, just like this is more like nesting of a declaration within an expression and a declaration within a command, to create a block. Similarly, you can nest a declaration within a declaration to create a new declaration, right. So, the important thing is, so we look upon this in the context of a functional language, because then we do not have to worry about store. Okay, it is just an extra complication. To understand what these things mean does not really require to know whether you are dealing with a functional language or an imperative language. You can deal with them independently, right. Yeah, that is a good question. So, we will just come to that. So, let us look at these three operators in some detail, right. So, if you look at these three operators in detail, all these three are what might be called composition operations. I mean, you have the only composition operations that you learnt are function compositions in mathematics, and thereby also in programming. So, these are, sequential composition of declarations is also a composition operation, and the other two can also have the same status as composition operations. So, let us look at it in the analog of what we would do with respect to functions, right. So, if you have a simple mathematical function and you actually compose two functions f g of x, right. So, this is a simple composition of functions in mathematics, where we will assume that the types of f and g are such that you can actually perform these compositions, right. So, for example, g, if g is from some set a to b and f is from b to c, then this f of g of x, this composition of f and g would give you an element of c, right. So, this is how simple mathematical composition works, right, and you can diagrammatically look upon this as something in which the value x comes into some black box G, gives you maybe a value y, which is fed into the box F till you get an output Z, right. This is how simple composition works. You can also look upon this as a series connection of these boxes, right. You have learned about the series connection of resistors, so you can also connect these boxes in parallel, right, just like you do it with resistors. So what we could do is, we could actually consider these series and parallel compositions of declarations viewed as boxes. So, the effect of so given an input environment rho, the effect of d1 semicolon d2 is exactly like the effect of just like the semicolon operation on commands gives you a sequential evaluation of the two commands, right. So, C1 semicolon C2 is like putting in the input state into C1, getting a state out sigma, let us say an intermediate state out of C1 and putting that into C2 and getting a final state out, right. So, just a sequential composition, so it is really a composition operation, that is why I clearly mentioned once that we will use semicolon as a composition operation rather than as just a terminator. It is not a mere syntactic sentinel to mark the end of a command, okay. Though more and more programming languages are actually taking the view that sentinels are more important than having it as an operation, since most people understand juxtaposition itself as an operation, you can eliminate this and use it instead as a terminator, okay. But since we are dealing with composition operations, so I would like to view it explicitly as a composition operation. So, the effect of an environment rho on the box D1 is to produce temporarily at least an updated environment. So, this box D1 actually produces a little environment rho 1, and all this is supposed to be in the context of some larger command or an expression and so on, which temporarily is going to be evaluated in the row in the environment row updated with row 1. And of course, the effect of this is to create a new updation where of course this updation operation is left associative. That means you can assume that this bracket is here. Yeah. So take the updated row 1 and update it further with row 2, right. So if you were to connect things in parallel, then what it means is that the same row is supplied to actually both D1 and D2 in a fan out fashion, and these D1 and D2 independently produce new environments row 1 and row 2, and whatever is the rest of the command or the expression that is to be evaluated is actually evaluated in this composite environment. However, how you compose this, how do you compose this environment? I will just take the union of the two environments.
If we have some common variables,
yeah. So the main restriction that we require is that we should not have the same variable declared, the same name declared in both D1 and D2. If you have the same name declared in both D1 and D2 with different expressions giving them values, then of course there is a question of what does that identifier denote in this composed environment, right. So that is a syntactic restriction that you have to impose, right. So let us just
we could have always taken the disjoint union. Why not?
No, we could have taken a disjoint union, but if you were to take a disjoint union, then what it means is that you have to introduce extra syntax to distinguish between the two identifiers with the same name. It's not a big problem. It's not a very big problem because this is something that is used. The record selector kind of syntax is often used to distinguish different identifiers bound in different declarations. Yeah. So very often in languages like Ada, you can override the scope rules by using a record selection method to make available an identifier that has been redeclared in the current scope, but you do not want it hidden from a previous scope. Okay, so a simple record selection method can be used to get rid of that, but let's not complicate matters. So let's just impose this restriction which actually ML imposes. So unlike Ada, for example, ML has this restriction that this D1 and D2 should actually be disjoint. Should be disjoint in the sense that the identifiers they declare should not have the same name. There should be no common names in the two declarations D1 and D2, right. So I had actually an example for that. Right. So what so the objection raised by him is something like this, right. So either you take disjoint unions and allow for a new operation called field selection, which explicitly tells you whether this y, to disambiguate this y, but then what, in order to be able to do a field selection and explicitly disambiguate this y, what it means is that then this declaration has to be named, okay, and this declaration also has to be named. Unless they are named, there is no way a user can actually disambiguate this. But once you have named them, then what it means is that you have to have these declarations separately named, let us say as functions. Okay. So, and these are complications, for example, the ADA manual has gone into great detail to clarify, right. So, you can actually scope rules can be overridden, the hiding, the hole in the scope concept which we spoke about can be overridden by using a record selection kind of operation, which tells you that which basically says that if an if you have two blocks, if you have an identifier x declared in both blocks and you want to use this x, then this block should have a name. Let me call that P1, let me call this P2, and you want to use the x that is in P1, then the ADA syntax actually allows you to do a record selection of this form. So, the hole in the scope created by this new declaration can be overridden by a record selection mechanism. Okay. But what it assumes is that you actually have a name for this block. You have to have a name for this block, and which means that you are creating a new environment with this name. This name is associated with this entire block, and only then. So, it's an extra complication. Very often very many people believe that scope hiding can often be used deliberately to ensure that you do not make any confusing assignments, whereas using this record it is quite possible that one might just use x, intending x, without actually performing the record selection, and one might create an error and it will not be detected. So, lots of people believe that as a part of security of programming, the hole in the scope concept is an important concept and should be adhered to and should not be overridden by such mechanisms, right. Okay. So, this example clearly illustrates, you know, what can happen if you have this, and you can try it out on the ML system. You should get an unresolved error, you should get some error, syntactic error. It's a matter that can be syntactically resolved. Okay, the last composition is somewhat more tricky, and this does not fully explain what exactly happens, right. So, you have a series connection of declarations, you have parallel connections of declarations with the added restriction that the identifiers they declare are disjoint, and then you have this nested declaration. So, D1 is nested within a larger block D2. Okay. So, the effect of this is that this input environment rho is really required for D2. However, D2 is so complex that I cannot adequately express the declarations in D2 without introducing fresh new names. So, what I do is I introduce a declaration D1, but which is purely local to D2 and is not visible outside D2. So, the effect of this purely local D1 actually creates a little new temporary environment rho 1, and in this updated environment rho 1 you elaborate the declarations in D2. And the effect of this is that since this is totally temporary and is bound by a scope which lasts only up to the end of D2, what you get is not something of the form rho 1 updated with rho 2, but what you get is just rho updated with rho 2. That rho 1 was purely intermediate in order to facilitate a structuring of the declarations in D2. Right. So, this is the difference between a pure sequential composition and a nesting of declarations. So, let's just look at a simple example to see what this means, right. So, here I have got 3 examples, one for each kind. So, here let us quickly look at this. Let x equals 3 in let x equals 5. Of course, my ML notation is faulty, but that is deliberately so. I do not want to be worried about syntax too much, and usually there would be val or fun reserved words used, but I do not want to use all that. So, let x equals 3 in let x equals 5 semicolon y equals 6 star x in x plus y. So, this is an expression, this is an expression block in which you want the value of x plus y, where this x according to the normal scope rules refers to a binding created by the innermost enclosing scope which has a declaration for that x, and the same is true for this y. These two declarations are sequentially composed. So, what it means is that you start with x equals 3 initially, you have redeclared x to 5. So, in the updated environment you have x equals 5, and in that updated environment y is evaluated. So, the x that y uses in its for the binding of y, the x that is used is really the x in the updated environment where x equals 5, and in the same, after having created this environment row 1 updated with row 2, you evaluate this expression. So, this x would just refer to this x and this y would refer to this y, and you would get an answer of 35, right. On the other hand, if you had a parallel or a simultaneous declaration here, then both these declarations are elaborated in the original environment that is created. So, both these declarations are elaborated in an environment in which x equals 3. The result of this declaration is to create an updation x equals 5, and the result of this is to create a binding y equals 6 multiplied by the value of this x, which is 18, and this x plus y is evaluated in this scope, and so therefore it takes the value of this x and the value of this y to give you an answer of 23, right. So, supposing you had a within construct which is really like a local construct, then what happens is that you have x equals 5 within y equals 6 star x. So, this declaration of x equals 5 is purely local to this, to the elaboration of this declaration. After that, this declaration loses its meaning. So, the x that is referred to here is the original x that was available there, and the y is whatever this y is. So, you get an answer of 33. So, we will look at the semantics of these declarations next time.